ammonia is whatever it was.
That's a PKB.
Right, PKB, so sorry. Where it was the 4.74. And I had a decent handful of you kind of ask, where do I start from? You're starting from the identity of this guy. Okay.
Plus water.
Plus water, exactly. Plus water. So you're looking at that thing and you're realizing that it is a salt. And so now you're going to have to break that salt down and decide, are we working on the cation or are we working with the anion? And hopefully from our previous little Zoom meeting, you realize that chloride is the counterion of a strong acid. So it is essentially has no basic properties whatsoever. We are not concerned about it. I believe on Tuesday it was Daniel who said, oh, poor chloride, nobody cares. Yeah, pretty much. Nobody cares, Daniel. Not chloride. He's just there to spectate. Okay? So you are looking at this thing. This is the conjugate acid of a weak base whose PKB was given to you. So you're right. It sounds like that's Emmanuel. Is that Emmanuel you talking?
Yeah.
Is that you? Okay. You're absolutely right, sir. That's what you're looking at. Is what does this thing do in water? And you're like, well, okay, I just got to get that out of the way a little bit because you think I don't do well writing on the chalkboard. I sure don't do well writing on this whiteboard. But so now you realize that that's the weak acid. It's dissociating in water. We're making the conjugate acid of the water and the conjugate base of that acid. And now you're ready to set up that table. All right. You've got the 0.35. That's your initial. You know what to do from there. But realize that all I gave you was a PKB for this guy. Well, you're going to have to figure out the Ka for this guy. But you know how to do that now because pKa plus pKb equals 14, or Ka times Kb equals Kw. All right. Oh, and everybody say good morning, Bob. Bob has joined.
Hi, Bob.
Bob has joined the chat.
I love that.
Yep, here he is. He's like, what are you doing? Anyway, so that will hopefully get you started on that one. Okay?
Doc?
Yeah.
So for that problem, I actually, instead of solving for H3O plus, I actually solved for OH. I set it up to solve for OH instead of like hydroxide, I think. And then I just subtracted it. I don't even know, but
Yeah, I did the same. To find the pH, then you did the 14 minus whatever you got, right?
what did you get for your final pH?
Should we say it in the chat?
Yeah, go ahead. You can say it in the chat.
So I got 9.2.
Oh,
And you
well,
see
I got 13.5 too.
And guess what? You're both wrong.
And
That's the problem. If you set it up as you just described, and that is the most common error, if you set it up that way, guys, you don't have an initial concentration. The initial concentration, that 0.35, is for the ammonium, not for the ammonia. You don't have an initial concentration of the stuff you just think you set up the equilibrium for. You don't have any ammonia, right? If you set it up with ammonia, that's, well, if one of your products was OH minus, then that means you set it up for the equilibrium of ammonia with water.
Yeah.
Guess what? I didn't give you a concentration of ammonia. They're not the same.
Ouch.
Got it?
Yeah. So how? I'm not sure how to go about it if that's the case.
Can you see my whiteboard?
Yeah.
That's how you do it. You have to start with what you were actually given in the beaker. And what you were given was this guy. And so you have to follow the path of what is he doing in water. Well, he's a weak acid, so he's going to make hydronium.
In an unknown quantity, in an X quantity.
You're right. You're going to do, right? It's going to be the initial zero. Right, then you're going to do your thing. Right?
Yeah.
Yeah. That's how this one has to be set up. You don't have an option. You don't know how much ammonia you have.
So once we have the Ka, we set the Ka equal to the ratio of the products over the
Yep.
initial.
Same old,
Okay.
same old. Ka for the ammonium cation equals x squared over 0.35 minus x. But luckily, if you've proceeded to calculate the Ka, you know that you can take the hack. X is
So-
negligible.
I had set it up like that, but in the wrong kind of direction, but I still followed x squared over 0.35, and maybe I calculated the Ka wrong, because otherwise I should have gotten the correct answer.
Yeah, you can. I'm getting a Ka of 5.5 times 10 to the minus 10.
Well, I got 5.88 times 10 to the minus 10.
Let me see. It was a 474. Boopity boop. And then that's that. Oh, I should have done it the other way. There, I like that one better. Now I'm getting 5.5 times 10 to the minus 10.
Oh yeah, I see my mistake. Okay.
Okay,
Yeah.
cool.
But that should have been correct. And then I do the square as x for the square root of whatever I get times the initial concentration.
Correct.
And then the negative log of that, and then 14 minus that.
And so you work your way through that.
Do you need to do 14 minus because you have the hydronium ion concentration? Should
Yeah,
that give you the
yeah.
pH
Yeah.
without doing 14 minus?
Well, that's the pOH though, and then I have to do the 14 minus that to get the pH.
No, don't solve for pOH. That's the point. You're not making any hydroxide.
Interesting.
It's a
we
weak
have
acid.
hydronium ion, so that would be H plus ion, which is
It's already
the
H plus.
definition of pH.
Yep. You have no hydroxide in the beaker, guys. Ammonium, right, NH4 plus is a weak acid. It's going to make hydronium. It is your only option. That is the only equation. Yes, Bob. That is the only equation in play.
So I don't need to subtract.
Nope.
So to get Ka exactly, how do you solve for Ka using Kb? Using the equation for the ice from the ice table.
How do you get Ka from Kb?
I know this, but I'm forgetting right now.
Okay. Kw
Oh, that's
equals
right.
Ka times Kb.
Mm-hmm.
So if I don't subtract my, then what I get is 4.9.
Yeah, but you need two sig figs. Yep.
Okay, so 4.86.
Yep, there you go.
Oh, okay.
There it is. All righty. These are the kinds of things we're going to run into more and more and more today, ladies and gentlemen. So kick it around. Yeah, you just figured out, right? You just heard what the right answer was. Make sure you can get it.
Wait, what was the answer?
She just said it. The right answer for number 6, guys, is 4.86. Make sure you can get it.
Yeah, I'll make sure.
Okay. So look, now I want to go back to Bufferland. All right. So I'm going to get in there and share something else. Where am I? Back to Bufferland. Oh, wait a minute, Aaron, then what's the 4.74 for? Oh, Aaron, the only way you can get Ka is from Kb, right? The only way you can get Ka of the weak acid is from the Kb of the weak base. Well, I didn't give you the Kb of the weak base. I gave you the pKb of the weak base. From the pKb, you can get the Kb. From the Kb, you can get the Ka.
And once you get Ka, you just set that equal to the
Right.
ice table.
Exactly.
X squared
Once you've
over
got
0.35.
Ka, you just ice table it.
Gotcha.
Okay.
Mhm.
Yeah, but that's your only way to get the Ka for the acid you're working with, because you're not going to find that one in the appendix. You're going to find the Kb for the ammonia, not the Ka for the ammonium ion. They're like that a lot. All right, you guys ready for this? I try and attempt to turn this bugger into, I'm going to do it as a slideshow. This is where I stopped on Tuesday, and I said we'll come back to this because this is where we need, again, it's almost all contextual. You guys are, setting up ice tables, fine, but the question is going to be, what does the table look like? So I wanted to go back to this buffer and calculate the pH of the buffer, and then stress the buffer. That's the point, right? That's the point of making buffers. And almost every single one of you, in what you want to go on and do with your lives, for the most part, you're going to care about buffer systems, because organ systems, environmental systems, industrial systems are going to have optimal pHs at which they operate. And you can help with that by setting up the correct buffer system for them to operate in. So you really kind of do just the whole buffer calculation thing is almost more important than the titration calculation thing, but they're so darn interrelated that we kind of got to do it all at once. So take a look at 17.8a. And this one is hopefully not too bad. You really got to read carefully. It says you've got what, 0.15 mole of acetic acid and 0.195 mole of its conjugate base. So that should be screaming to you, buffer, 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 buffer. Anytime you have a mixture of a weak acid and its conjugate base, it's a buffer system. Oh, Bob sees something. What does Bob see? Oh, I see what Bob sees. Bob's doing his job again, ladies and gentlemen. I'm assuming you can hear him yelling.
Yeah.
He's doing his job. Anyway, but once you spot this thing as a buffer, please, please, please use the Henderson-Hasselbalch equation. All it's asking for is, what is the pH? Well, pH equals pKa plus the log of the conjugate base over the acid. And you can do it in molarity, or you can do it in moles, because they're in the same container. So as long as you know the moles of each, you also, as long as you know the moles of each, as long as you know the ratio of the moles of each, you also know the ratio of the molarities. Yes, the official definition, let me go to my favorite color here. The official definition of the Henderson-Hasselbalch is, of course, in molarity. All right. But if it's a buffer, they're in the same container. So if you know the mole ratio, you also know the molarity ratio. If it's, 0.15 mole of acid per liter and it's 0.195 mole of base per liter, well, yeah, they're both in the same liter of stuff. So please, please, please do yourself a favor and make it easy. pH equals pKa plus the log of the conjugate base over the acid. Watch your sig figs. It's 2 to the right. It's 2 to the right. Okay. Even though we had a few more sig figs in here, we were stuck with the 2 to the right here. Okay. And just crunch through it. But here's the cool part. How does this buffer do its job, right? The point of a buffer is when there's an external source of strong acid or strong base, the common ion effect kicks in, Le Chatelier's kicks in, and the buffer is able to compensate and minimize the detrimental effects of the addition of that strong acid or base. That's the point of a buffer, is to minimize the pH change when extra acid or extra base is added to the system so that the system doesn't die. Again, all these environmental systems, all these organ systems, they operate in what is a very narrow pH range. And that's why we care. So on part B, we're going to take a look at, hi, Daniel. Yeah, I was missing you, Daniel. There were no sarcastic comments yet. Anyway, here we go. Take a deep breath and notice that this table has changed. The Henderson-Hasselbalch equation kind of lets us skip that ice table. You can do it with the ice table. But now we're doing something else, guys, okay? You're taking this buffer and you're stressing it.
Ooh.
And you're stressing it by addition. Remember, this and this are in the same beaker. And they're just chilling out, giving us a pH of whatever that was, 4.86, 4.84, whatever it was on the previous slide. And it's just chilling out and doing that. And now somebody comes along and dumps a bunch of strong base in the beaker. That addition of strong base, if it was in pure water, would send that pH skyrocketing and would cause base burns. So now the question is, what does the buffer do about it? Okay. Yeah, exactly, Michael. Ouch. So there's a couple different ways to go about this. Your textbook does a very good job of it. And then the PowerPoints, to be blunt, sucked. So I've done a
Surprising.
lot. What's that?
Very surprising.
Yeah, big surprise. Woo! So I'm going to reintroduce you to something that actually the textbook talked about in the Chem 111 portion of how to do stoich. Please notice this equation up here. This is literally what's happening. We've just tossed a whole bunch of sodium hydroxide into the beaker. Well, hydroxide is a strong base. What's it going to react with? Right? Bases react with acids. But this one's strong. So the reaction that ensues goes one direction and one direction only. Ladies and gentlemen, this is not an ice table.
Oh.
This is not an ice table.
Hmm.
This is a stoichiometry table. I call it the initial change final table. So you'll see over here for me on answer keys, instead of saying ICE, I will say ICF. And what ICF means is that the reaction is not reversible. It is going in one direction and one direction only. And we are literally doing limiting reactant stoich. So take a look at this reaction. If I started with, in my buffer, 0.15 moles of the weak acid and 0.195 moles of the weak conjugate base, and I throw in this much strong base, the reaction is going to go to completion until the limiting reactant is used up. Welcome back to Chem 111. Look at the 2 mole amounts and tell me who the limiting reactant is.
HC2H3O2.
No, it's
No. Sorry, I missed the zero. I missed the zero.
Okay, you missed the zero. Okay, now this guy's the LR. So he's going to get in this reaction that is now only going from left to right because it is a strong base. It is not a weak base. It's going to all get used up. Look, it's 1-to-1 stoichiometry. This is not Chem 112. This is Chem 111. He is the limiting reactant in this reaction. He's going to get all used up. And if the stoichiometry is 1-to-1, how much of the acetic acid is going to get used up?
All of it?
No. Look how much limiting reactant you have.
0.03.
This is limiting reactant Chem 111. If you only have 0.03 moles of one reactant, the reaction stops after it is used up. This is not an equilibrium. This is stoich. If you have only 0.03 moles of one of the reactants, well, that's what's going to get used up. If it is 1-to-1 stoichiometry, then that's what's going to get used up of the excess reactant. So this one's the LR, and this one's the excess. And so you got to figure out how many moles of each you started with, how many moles of the moles of limiting reactant always get used up, and then you've got to do the math. If I had started with 0.150 moles of the excess reactant, and I use 0.03 moles of it, somebody just keep double checking my math. 0.15 minus 0.03 in my book is 0.12. Yes?
Yes.
And it's gone. It's used up. This was not reversible. But we got the same thing going on over here. This is a product. It irreversibly makes that many moles of that. This is Chem 111 limiting reaction stoich. The moles of product formed comes from the moles of limiting reactant used up. And if I take 0.195 and add 0.03, somebody do the math for me. 0.1. No, so 0.2. Quick, somebody. 0.2 what?
215.
215.
225.
225? Yeah, 225.
Yeah.
Right? 0.225. Look what's happened. And again, we don't care about the water. Look what's happened. I've changed the ratio of weak acid to weak base in my buffer. The strong base is totally gone. It was the LR. It was the limiting reactant. It's gone. But in getting consumed by the weak acid, it changed the proportion of weak acid to weak base. Okay? Right. Nobody cares about the water. It's not because we don't need it, Michael. It's because there's so much of it, we can't even tell that there's been a change. So we just changed the proportion of weak base, weak conjugate base to weak acid in that buffer system. And now we turn around and ask again, hey, what's the new pH? Well, you now have new proportions, but it's still a buffer because we still have conjugate base, we still have conjugate acid. As long as these don't go outside the range of about the proportional range of about 10 to 1 in either direction, you've still got yourself a buffer. When they go beyond the range of about 10 to 1 or 1 to 10, then we start running into trouble and it really can't buffer anything anymore. So next slide, what's the new pH? Oh, by the way, I've also put in the finished PowerPoints, okay? Well, new proportions. Same pKa, because it's the same weak acid, it's still just acetic acid, but we changed those proportions. Run it through the Henderson-Hasselbalch again, and you've got a new pH. What was the original pH? 4 point what?
0.86.
4.86. So it went up from 4.86 to 5.02. So we went up by what? 0.16 pH units. And maybe you're thinking, well, that's, seems like kind of a big jump to me. No, it's really not. You threw in, and I did the math, 0.03 moles of sodium hydroxide is, Daniel, are we on the edge of killing the buffer? No, actually not yet, because this one's only basically 2 to 1, right? Not even 2 to 1. If we get to 10 to 1, then we're on the edge of killing the buffer. So we would have had to have added a whole lot more, almost 10 times more sodium hydroxide in order to kill the buffer. And then we couldn't have used the Henderson-Hasselbalch either, because it wouldn't be a buffer. Yeah. What you want to kill, don't kill the buffer. Buffers are our friends. Anyway, so note that it used to be, when you first put the buffer together, the pH was 4.86. You pummeled it with some sodium hydroxide, but the common ion effect went into effect. We compensated for it by simply making more, right? The weak acid, the acetic acid, simply reacted irreversibly with the strong base to make more of the acetate. And so we saved the organ system because this range of pH change is probably okay. It's only 0.16. And if you're thinking, whoop-de-doo, big deal, try this. Let's say it wasn't a buffer. Let's just say it was pure water. And we tossed 0.030 moles, so the exact same amount of sodium hydroxide, into a liter of pure water. Well, where's the water start at? If it's pure water, what's its pH?
7.
7.
7.
So we would have started at 7. Now we chuck 0.030 moles of sodium hydroxide into a liter of water. So we have 0.0300 molar. 0.0300 molar hydroxide. Run the pH on that puppy. And you get 12.48. It started at 7, pure water. You chuck the same amount in, and it went screaming up to 12.48. That would kill the organ system. If that was your blood and there was no buffer in effect, chucking 0.03 moles of sodium hydroxide would have turned your blood literally into Drano. Okay, what a buffer can do is phenomenal. And this is why we care. It will literally, by an irreversible reaction of one of those two conjugates with the strong substance, it will compensate. We'd be stuck with a whatever that delta is, 5.48. 5.48 pH unit increase versus a 0.16 pH unit increase. This is why we care. Okay? This is why we care. And of course, the next problem solving assignment coming out will have you do this. Again, if we were going to try and kill the buffer, adding the 0.03 moles basically change that proportion from 1-to-1, not quite 1-to-1, to closer to 2-to-1. So we probably would have had to have added probably 0.3 of a mole. Okay, yeah, Sophia.
So I'm thinking about possible questions, and just for my brain, could you please explain, in case, for example, a question asks, how much do you need to get the pH from 7 to, 12.48? How would that, which kind of information would we be given, and how would we work backwards?
Do you want that question asked, how would we get a buffer of a specific pH?
It's like, I'm thinking this question just reversed. So like if we had the answer and we had to get back to what we need.
Oh, got it. If we were in pure water, you'd say to yourself, well, okay, I have a pH of 12.48. It came from hydroxide. So, my hydroxide ion concentration would be equal to 10 to the negative POH. Now this is a pH. So quick, do the math. If the pH is 12.48, then the POH is 14 minus 12.48. What is that, 1.52?
Yeah.
Yeah.
Okay. Oh, okay.
Okay.
Got it. Clear. Yeah.
Okay, cool. Yeah. And I realized, and I'll have to remember to put this either in the slides or just as a even just as a one pager that you guys can look at. I have somewhere in some old PowerPoint just a kind of a mind map, so to speak, of all these relative relationships. And I will just post that, and you can kind of sit there and go, oh yeah, this is the relationship between pH and POH. Oh,
That
this
would be
is the
great.
relationship between POH and
that'd be
OH
nice.
concentration. This is the relationship. This is the relationship. And if I don't do it in the next day, somebody remind me, okay? I know I have a good graphic of that, but the sapling PowerPoints, or the IGC PowerPoints, did not have it. And so I've
Okay.
totally spaced out doing anything about it. Okay. So somebody remind me, and then you'll just have this little template cheat sheety thing staring at you. Okay.
Okay.
Okay. So that kind of finished up the buffer thing. And I just really wanted to go through that, if for no other reason than for you to be impressed by what a
no,
buffer can
stop.
do for you.
Nina, stop that.
Okay. Right. Oh, so many relationships. Are they practicing
God.
social distancing? Yeah,
Nina,
I'm
stop.
not really, to be blunt.
No.
Let me see.
Cat, stop, please. Oh God.
Hey, somebody, you need to mic up. All right, I'm going back to, I hope I'm finding, no, that's wrong. Oh, there we go. All right, I'm going back to, or starting the next PowerPoint. Come on, wake up, baby. There we go. So now this should be the wonderful world of, yes, titration. Okay. Um, yeah, run. I'm also, by the way, thinking of putting out an extra credit assignment out there somewhere, asking for your favorite coronavirus meme, but realize I've got a great one. It's kind of rude. And we'd have to set some rules. I have a Winnie the Pooh coronavirus meme that I've turned into a poster.
Can we see it?
You have to, yeah, there's a word in it that would be professionally inappropriate.
Oh.
Maybe I could, block it out. Anyway, I'm thinking about it. We'll see. We may as well keep a sense of humor about this. But anyway, okay, so here we go. Was there anything else? That was the end of 17.2. You guys are going to be a little annoyed with this problem-solving assignment that's coming out because you're going to feel like you don't know what you're doing, but we're going to address it on Tuesday, and I'm going to prove to you that you do know what you're doing. Okay? But what I really need to do is get through some of these titration calculations so that you guys can chew on these as well. And then we may end up spending all of Tuesday just chewing on problem solving. All right. We're going to do this in two formats. I'm going to walk through one straight instructional example. And then, like I said, I apologize for getting it up so late. For those of you who were able to get your hands on that handy dandy titration guideline template page, we're going to start filling this bugger out. And you're going to use it literally as a template for doing any other equivalent problems. So we're looking at only two scenarios. We're going to either titrate strong acid with a strong base, or we're going to titrate a weak acid with a strong base. Okay? Oh, okay. We'll grab that one later, Michael. I'll probably have you guys upload them. That's what I'll do. Anyway, so away we go. Reminders, ladies and gentlemen, what the heck is titration, right? Titration was from Chem 111, where we did the stoic. And we said, let me get my pen back up. We said HCl reacts with strong acid, reacts with strong base, irreversibly to make water and a salt, right? And now you have so much additional information that we can follow the progression of the pH values as we titrate. In 111, your only interest was what is the equivalent point, right? What is the equivalence point?
Yeah.
You were using it, you'd have what? You'd have the known volume of this, and you'd have the known molarity of this, and then you'd have a volume of this, and your question was, what was the molarity of that? And you had the balanced chemical equation, and everything was fine. And that's what you use titration for. I don't even know what Rolle's theorem is, Michael. Anyway, we're going to go into it in much greater detail now. Now the question's going to be, what is the pH at various points along the titration process? Starting with strong acid, strong base. And honestly, it doesn't matter what these identities are. We are going to stick to one-to-one stoichiometry. But so we're just basically going to be doing this. H plus OH minus makes water. And all the stoich's going to be based on that, but we're going to keep stopping and recalculating the pH at various stages along the titration. Again, in Chem 111, all you cared about was that one. Well, now we care about 4 regions. Before the titration starts, before the equivalence point. So that's the equivalence point. We care about it before the titration starts. What's the pH? What's the pH before the equivalence point? What's the pH at the equivalence point? And then what is the titration, or what is the pH after the equivalence point? At any given volume past the equivalence point. Whoops, sorry. I'm having a little pen trouble here again. Come on, pen. Come on, baby. Now we'll go back. There we go. Sorry. Anyway, this, ladies and gentlemen, has absolutely nothing to do with buffers. So put the buffers on the back burner for a moment and let's go play around with titrating. What you saw was a pH versus volume. Let me go back again. A pH versus volume graph of this titration curve, and they do call it a curve. So 4 regions, and this is how IGC does it, and then you're going to notice that I change it, and instead of doing A, B, C, D, I'm going to do regions 1, 2, 3, 4, but they correspond. Look, region A, it's easy. The titration hasn't started. All you have in the Erlenmeyer, and again, I'll remind you, remember how this worked? If I go all the way back, remember, we'd have the acid in here. We'd have the base in the burette, and we'd add the base to the acid. Yes, you can do it the opposite way. We're not going to. Well, at least we're not going to do the calculations. If we can do it in one direction, I'm happy. So look, before you start the titration, this is a trivial calculation. What is the pH? Well, it's just the pH, right, of the strong acid. It's negative log of the acid concentration. You don't need to know volume. You don't need to know nothing. You just need to know molarity. So that's easy. Now, remember, this is strong acid, strong base. So this does not fall under the definition of buffers. Strong acid, strong base. You cannot make a buffer out of a strong acid, strong base combo. It's got to be weak acid, weak base. So this one's easy. We'll do it in a moment. That second region, region B, is anywhere between your first drop of added base and the equivalence point. Well, this reaction, which is up at the top of the page, is irreversible, guys. So region B is all about the limiting reactant. If we are before the equivalence point, the limiting reactant is going to be the base. If we haven't hit the equivalence point yet, there's less base than acid, and it's a limiting reactant problem. But what you have to figure out is how much excess reactant is still in the beaker, or still in the Erlenmeyer. And so that's why we start calling upon those initial change final tables again, because we've got to do the limiting reactant stoich. I'll give you an example in a minute. This third region, good news, for strong acid, strong base titrations, when you hit the equivalence point, it's 1-to-1. There's neither acid nor base. You've made water and a salt, and guess what the pH is for strong acid, strong base? Okay. I need a thumbs up.
Yeah.
Yeah, okay. Then after you've exceeded the equivalence point, so now there's going to be more base than acid, it's going to be another LR problem. The LR is going to be the acid, and you're going to have to figure out the pH from the excess of base that's present. So here's how this plays out every single time. Strong acid, strong base. We've got a molarity and a volume. We've got a molarity, and then we got a bunch of different volumes. So there's region A, there's region B, there's region C, there's region D. All right? Don't make region A hard. You have 0.255 molar HCl. Doesn't matter how much of it you have. What's the pH of 0.255 molar HCl? Quick, someone with a calculator. 0.255 negative log of. I got 0.593. Yes?
Yeah.
Yep. Okay, trivial. Because nothing's going on. I mean, all you got is a bunch of strong acid in a beaker. But now you start adding base. And the base and the acid react irreversibly. And you got to figure out, no, you don't even have to figure out. You know that the base is the limiting reactant because we haven't hit the equivalence point yet. Your textbook does a great job of this. The PowerPoints stunk. Basically, the PowerPoints talk you through it. I'm going to show it to you. What they've done. So now we've started adding base, and in this case, it was just 4 milliliters. This is a true statement. This is a limiting reactant problem. So you're going to have to calculate the moles of base in the beaker and the moles of acid in the beaker. You know that this is going to be the LR, and you're going to do the limiting reactant Chem 111 stoich. Again, like I said, these PowerPoints, basically write a dissertation about it. I'm going to show you the chart. But this is important. Take your, right? You know that. Volume times molarity equals moles. Volume times molarity equals moles. So you know how many moles of each you have in the beaker initially. They react. The limiting reactant gets used up completely. We've got some excess acid sticking around. You have to calculate the concentration of the excess reactant that's sticking around, and again, calculate a pH. They taught, like I said, I left this in here just because they talked you through it, but this is what you need to use. Look, you started with, and double check me, right? 25 milliliters of 0.255 molar HCl is this many moles of HCl. 4 milliliters of 0.15 molar OH minus is that many moles of OH minus. Do the limiting reactant math. Before the equivalence point, he's the LR. He gets completely consumed. You end up with no strong base in the beaker. The HCl is the excess reactant. We use up as much of it as we can. Yeah, we make an equivalent amount of water, but the water is not affecting the pH. So again, this is what I'm calling this initial change final stoich table. So now what you have in the beaker is this many moles of strong acid. And you're like, cool, I can take the negative log of 0.00578. No, you can't. That one's in moles. You need it in molarity. And oh, newsflash, the volume's changed. You don't have 25 milliliters of solution anymore. Wait, we actually have to count the water. We don't have to count the water. We have to count the volume. You took 25 mils of one thing and added it to you took 4 mils of one thing and added it to 25 mils of the other thing.
Yeah, it makes a difference.
You've got 29 mils in the beaker. It sure makes a difference to concentration. Molarity is moles divided by liters. You don't have 0.025 liters anymore. You have 0.029 liters. So what the next thing looks like, that's what that said. You have to divide the moles of the excess remaining acid by the total volume in the beaker, or in the Erlenmeyer, which was the original 25 mils from the acid solution plus the 4 mils you added. Yes, it makes a significant difference. And yeah, most of it's now water because everything we did neutralized. It's water, but right, it's water and a salt plus the excess acid that didn't get used up yet. So you can double check my math. Oh, by the way, they do it this way in the textbook, but they screwed up the sig figs in the textbook. I kid you not. As far as I can tell, this is right. You can double check me. But now I have a new molarity of the acid Of course, it's gone down because some of it was neutralized by the strong base. It used to be 0.255 molar. Now it's 0.199 molar. Take the negative log of it, get yourself a pH. That process, and so yeah, it's gone up. Not a lot, because you didn't put a lot of base in yet. But yeah, it's gone up. So anytime at any volume, I shouldn't say time, any volume before the equivalence point, the acid's going to be the excess reactant, the base is going to be the limiting reactant, and you're going to have to figure out from the stoich what the concentration of the acid, what the new concentration of the acid is, take the negative log of the acid concentration and get on with it. We could have done, let me make sure I don't screw this up. We could have done, 7 mils. And you would have set up the same kind of table. The KOH still would have been the limiting reactant. You would have figured out how much of the HCl did not react, calculated a new concentration, a new molarity based on the total volume of the two solutions in the beaker, and you would have taken the negative log of that new molarity. Anytime prior to the equivalence point, this is how you're going to do it. Okay? You're like, really? Yeah, really, sorry. So now we get to the equivalence point. By definition, ladies and gentlemen, what does that mean? Oops, just screwed it up. Equal molar amounts, right? Neither acid nor base. Neither acidic nor basic. We have totally neutralized. There's not an excess of either. So congratulations, if it's a strong acid, strong base, your pH is 7. All you've done is water and a salt.
And that's always the case, right?
For strong acid, strong base.
Okay.
For strong acid, strong base, it is always the case. By the time you get to the equivalence point, yes, that means you have to know what the definition of equivalence point is. You get to there, it's 1-to-1, acid and a salt, neither acidic nor basic, pH 7. Right? The K plus is the counter ion of a strong base, so it's not acidic at all. The Cl minus is the counter ion of a strong acid, so it is not basic at all. The only pH you get is the pH from the water, which comes from the 10 to the minus 7. Okay?
But it's not the case for strong acids and weak bases and vice versa, right?
Oh, no, that's why we're going to spend the next hour on that. Oh, no, then life gets really interesting. Okay? Look, if you're past the equivalence point, it's a limiting reactant problem again. Only this time the base is in excess. So we've got more moles of base than we do moles of acid. So now this solution goes fantastically basic. Again, the PowerPoints, they kind of wrote a dissertation and walked you through it, but they said, look, if you've done a total of 50 mils of KOH, well, you figure out, you do 50 mils of KOH times its concentration, you've actually added that many moles of KOH to the beaker. Well, that's way in excess of the moles of HCl that were in the beaker. And so now you can see that this is going to be the excess, this is going to be the LR, and if we set it up in that cool little ICF table, this is what it looks like. This has never changed. The initial number of moles of the acid has never changed. It's 25 mils of 0.255 molar. But now you've done 50 mils of 0.15 molar base. It takes it all the way up to there. This guy's now the LR. This guy's now in excess. All of this reacts, leaves you with no acid in the beaker at all. an equal molar amount of that reacts, but now you're doing 0.0075 minus 0.003638. Yeah, sure, you're making a bunch of water over here. Whoops, sorry, that should be a 38. Sorry, that's my typo. And now this is what you're worried about. The water's not going to contribute to the pH. It's now going to be base. So now it's basic. But again, you know the moles, but what's the total volume now? Because I can't take the negative log of just the moles of base. I got to take the negative log of the concentration. Oh, Daniel, can it not what? Oh, no, it has to get interesting. Sorry. It does. You can imagine. I'm serious, people. If we can get through this on Zoom, we can get through anything on Zoom. Because it does get interesting shortly. All right, but the issue is here, yeah, this is moles of base. I need molarity of base. I'm pretty sure most of you can add 25 to 50 and tell me how many total milliliters there are now in the beaker.
75.
75. So you take moles divided by total liters, and you find out that the molarity of the base is, and that's the excess base that you added. All the acid's gone. You consumed it. You neutralized it. And so now you have a new molarity of base. That's the only thing left in the beaker besides the salt and the water. You take the negative log of OH minus, you get yourself a POH. You subtract the POH from 14. And big surprise, oops, sorry, big surprise, it's basic. You know, you've, no pun intended, you've blown it out of the water at this point. You just screamed past the equivalence point, and now the whole thing's basic. And you can again see it from the curve. We started way down here at point whatever. What was it? It was 0.25, right? 0.255. What did we get? We got a pH of, we started down here with 0.593. We got to here, it was about 0.7. Because the acid was still in excess, we got to here and it was pretty much exactly 7 as long as we were at 25 degrees. And we got to here and it was 12.7 whatever. Of course it was. Okay. So now, as much as you don't want to do it, we're going to do it again. And I mean, you can do what you want, folks. But I would strongly, 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 if you were able to print this guideline cheat sheet template thing, these numbers are identical. And I'm going to walk through this thing. Fair enough? Everybody awake, kind of?
Yeah.
Mostly? Okay. So this is one of my own design. I am going to take 10 mils of 0.5 molar nitric, and I'm going to start adding 0.4 molar sodium hydroxide to it. So you've got the delightful strong acid plus strong base makes water. Classic, traditional Chem 101 stoic. Calculating pHs as we go along. So to begin with, region 1 or region A, I don't care what you call it. You'll notice on the other slide, I changed them and I numbered them. Hang on. See? 1, 2, 3, 4. Region 1, the initial pH is simply the pH of the nitric. Just do it. Negative log of 0.5 to 2 sig figs. To 2 sig figs. Negative log. And that's it. That's it for region 1. There's nothing else to be done because there's nothing else in the beaker. There's nothing else in the erlenmeyer. Now let's add 5 milliliters of 0.4 molar. You're going to have to go through and do the limiting reactant math. Somebody tell me how many moles of nitric I have. 0.01 times 0.5. I can do that math. Whoops,
Point
did I
zero
screw
zero
that
four.
up?
Yeah.
No, I'm right?
Yeah.
Okay. Now, tell me how many moles of hydroxide I just added.
Point 0.04.
Try again.
0.002.
Yep.
Oops.
Oops, right. And by the way, I did set this up so we're just fooling with 2 sig figs. Everything's 2 sig figs. So you can see that this guy's the LR. He's in excess. Do the math. He's going to react irreversibly, left to right. We're going to use it all up. And then this one's going to use up the same amount. We're going to have no hydroxide left because we're prior to the equivalence point. And we're going to have 0.0030 moles of hydronium in there. So now you need a pH. But we can't do the pH of this because this is in moles. We got to do concentration. So I do 0.0030 moles of H plus divided by the total volume, which is what? 0.010 plus how much did I put in?
0.015 mil.
Right. Exactly. Yeah, exactly. When you add them up, so right, the total volume is now 15 milliliters, not 10.
Professor, I'm still confused. Why is it 0.0020?
0.4 times 0.005.
Oh, it's 5 milliliters. Okay, sorry.
Yeah. Yeah. Okay. So yeah, you're doing that.
Yeah,
You're
okay.
doing those mole calculations. You're just doing volume times molarity. Volume times molarity.
it.
Volume times molarity. Okay.
Yeah, thanks.
Okay. And you're doing your thing. And if I do this, I get 0.003 divided by 0.015. I just got a molarity of, not molarity, Michael, milliliters.
0.2.
Yep, I just got a 0.2. So I get a 0.20 molar H plus. Take the negative log of that, get yourself a pH. And that takes care of region number 2. Oh, look, there it is. I did it. Yay me. And I do the negative log of that, and I end up with a 0.7 to 2 sig figs. Yes?
Yes, 0.7.
Cool.
Yes.
2 sig figs. Carry on. So that takes care of region 1. It's easy. Just negative log of the acid concentration. Region 2, do the limiting reactant math, get the pH of the excess reactant. Region 3, yay, it's the equivalence point. By definition, the equivalence point. And if you do the backwards math, you'll find out that at the equivalence point, you needed 12.5 milliliters of 0.4 molar sodium hydroxide to neutralize 10 mils of 0.5 molar nitric. That literally is what you did in Chem 111. You were constantly trying to figure out what was the volume or what was the molarity. Well, 0.0100 liters times 0.5 molar, 0.0125 liters times 0.4 molar, and they're the same number. 0.005. 0.005. So they've totally neutralized each other. We're the perfect stoichiometric point. pH comes strictly from the distilled water. Okay? So region 3 is always easy when it's strong, strong. Now, let's blow past the equivalence point. We know that the equivalence point would have been 12.5 milliliters. And so we've blown past that point. And you're going to have to set up that limiting reactant math again. And some of you, if some of you are doing it by inspection, that's fine. But if you're feeling like you're going to get yourself confused, please set up this initial change final table. This was still, we'd never have changed what was in the beaker, right?
Right.
Of the acid. But now we've added 15 mils of the 0.4. And I'm getting a 0.0060. Yes?
Yeah, I think so.
Yep. And so now this is the limiting reactant, and this is the excess reactant. And so we're going to, as always, we consume all of the limiting reactant. And because it's 1-to-1 stoichiometry, we're going to consume 0.005 moles of the excess reactant, and we're going to end up with a leftover of 0.0010 moles of hydroxide. And your pH is going to be based on that number of moles divided by the total volume, which is now 10 plus 15, which is a 0.025 liters. And you're going to get yourself a molarity of hydroxide. You're going to get yourself a POH. You're going to subtract it from 14, and you're going to have a pH. And that's how that works every single time. You get a 0.040 molar hydroxide. I get a POH, and I subtract that POH from 14 to actually answer the question, which was, what's the pH past the equivalence point? Essentially, what, 2.5 milliliters past the equivalence point. And again, for those of you who are looking at this and saying, can't I do this by inspection? Could I just do 0.00, 2.5 milliliters times the 0.0 divided by the total? Yes, absolutely you can. But if you're worried and you want to keep a very systematic process going, I strongly encourage these tables. And that fills out the first page of that template. Strong with strong. Oh, forgive me if I forget. How did I get the 0.006 moles of OH again? I literally did, Michael, 0.0150 liters, right? Because it was 15 liters of sodium hydroxide times its molarity. Liters times moles per liter, going to give me moles, right? And it's going to give me that 0.006. Okay, cool. Yeah, so you guys are constantly doing this. You're constantly doing liters times moles per liter to get the total number of moles so that you can figure out who's excess and by how much. And yes, you can do it outside the table. Just don't screw up the numbers. All right? And that gets us to here. IGC actually goes in and does an example of doing the opposite procedure, strong base, strong acid. So instead of having the base in the burette, the acid is in the burette. Well, guess what? It's the exact opposite process. You would start with base in the beaker. So your initial pH is going to be really high. Then as you're titrating, it's going to be the base that's in excess, so it's going to stay pretty high. You're still going to get to the equivalence point. It's going to be 7, and then when you blow past the equivalence point, your excess reagent is going to be acid, and it's going to go all acidic, and the pH graph looks exactly opposite. You get this from the concentration of the unreacted base. You'd get this when you did added a little bit of acid, so the acid was the limiting reactant and the base is in excess. You're still going to have to figure out how much excess base and what the concentration of it is. This is going to be a 7, and there at the end, that's going to be determined by the amount of excess acid that you blew past the equivalence point with. Do I, on a test, make you guys do it backwards? To be blunt, no. Does the sapling homework make you do it backwards?
Probably.
Probably. Are you going to want to devote a fairly significant amount of time to the section 17.3, 17.4 sapling homework?
Highly likely.
Probably. I really only have to assign one of each, but it takes a while, guys, okay? On the homework and exam, will we need to draw the chart? It might make you feel better, Victoria. Am I going to make you do it in a quantitative manner? No, probably not. All right. Now, on the titration lab report, are you using Excel to create a graph? Oh, yes, 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 you are. And you will be able to label those regions and you will be able to do all the math. I know if it were to be a question on an exam, or I do know in the sapling homework, it will actually give you all the pictures of the graphs and ask you what's the context. Is this graph, is this pH curve of a strong base being titrated by a strong acid? Or is it a strong base being titrated by a weak acid? Or is it a weak acid being titrated by a strong base? Because they do all look different. All right. You notice both on the strong acid with strong base and strong base with strong acid, you notice that this slope is pretty shallow. And this slope is pretty shallow. And then this, of course, is dramatic because we're so near the equivalence point. You'll see on the weak strongs that it's not as dramatic because we've got a buffer region. And so you can tell them apart. All right. Let me see. I think I know what's next. So there's that. Blah, 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 blah. All right. I say let's all go away for 5 minutes and come back, and I am going to walk you guys through this. All right.
All right.
But I need to go put more water in this glass. And I don't even know what time it is. What time is it, people?
12:30.
12:30. Yeah, that's about what this usually takes. Yeah, let's come back in three or 4 minutes, and we will blast through this. Okay.
All right.
Okay.
All right. Yay! I'm gonna mute myself somehow.
Well,
No, I do not. Alrighty, are we back?
I'm here.
Yep.
Did I screw anything up, or can you now see the 17.4 PowerPoints?
Yeah, it's here.
Yes.
Okay, cool. Oh, and by the way, Pasha, yeah, I liked your comment. Everybody go get some candy. Too bad I can't do drone drops or something,
Oh, that would be so cool.
Wouldn't that be hysterical?
That would be fantastic.
We actually have a prototype drone in the house, but I'm pretty sure it would not be dropping candy.
It's a problem. I'm finishing all my candy that I got for like a week in 2 days.
Sorry about that.
Oh, same.
Quarantine.
Okay, are you ready to forge ahead?
Yeah.
Okay. And again, we're going to do a couple of examples, but I'm just going to walk you through what does change. All right. For the strong, regardless of which direction you're going, you've still got those 4 zones. Before anything even starts, it's just the pH of the strong stuff. Before the equivalence point, it's the pH of the excess reactant. At the equivalence point, it's 7. After the equivalence point, it's the pH of the other excess reactant, or the newly excess reactant. When it's weak acids being titrated by strong bases, and again, Sapling walks you through both directions. I'm only going to walk you through this direction. This is the one I expect you to be able to do. Okay? Away we go. Victoria, you'll notice the graph looks a little different. Still the 4 zones here. Hang on, I got to get up for a sec. All right, I'm back. Still the 4 zones. In fact, I pulled this one from a different source because I thought it was a little more accurate. Saplings looks a little flatter. The IGC one looks a little flatter. I don't think it's all that accurate, in my personal opinion. But you will notice, once again, 4 zones. We're just going to go through 4 zones again. Before, what's the pH? Before you start titrating. Oh, man, I went to red. Hang on. There we go. What's the pH before you start titrating? What's the pH before the equivalence point? What's the pH at the equivalence point? And finally, what is the pH after the equivalence point?
Yeah.
Everything changes
No, please
except
go.
for this one. That one we're still going to calculate the same old way because it's going to be the excess base. And the pH is just going to be figured out from the moles of excess base divided by the total volume. Okay? But the other 3 are more involved. You know how to do it, but it's more involved. You do know how to do it. This one, the example was, it's acetic acid is what's in the Erlenmeyer, and sodium hydroxide was in the burette. And away we go. Please notice right off the bat, wow, the initial pH is a lot higher. Of course it is. It's a weak acid. It's a Ka problem. Oh, they give you this whole page of what changed. Yeah, whatever. Region 1, the initial pH. The initial pH is, hello, the pH of a weak acid. It's a Ka problem, ladies and gentlemen. I think you know how to do that. But you just can't take the negative log of the acid concentration to get the pH. It's a Ka problem. Find out what the concentration is. Set up the ice table. Yes, I promise that because these are weak acids, that anything you see from me, you will be able to take the hack, and it'll always end up being that the hydronium ion concentration is the square root, right? X will always be negligible. Okay, yes, we are hacking the system. X will always be negligible, so X will always be the square root of Ka times the initial concentration. It'll always, right, the Ka expression will always come out to this, okay? And then you just take the negative log of X and get your hydronium ion concentration. We'll do it again in a minute, but we've been doing that for like 3 weeks now, 4 weeks now. So, but that's region 1 before we've even started titrating. All you've got is a weak acid in the beaker. Region 2, somewhere between the initial pH and the equivalence point. Well, guys, you're adding a strong base to a weak acid. It's going one direction and one direction only. Strong base plus weak acid goes one direction. It's not reversible. So what you're doing is making a buffer. And you are in region 2 going to be able to use the Henderson-Hasselbalch. You'll see in a minute how. So region 2 is going to be a buffer. It's going to be the Henderson-Hasselbalch. Region 3, the equivalence point. You're like, it's 7, right? No, it's not. Because at the equivalence point, the only thing in the beaker now is weak base. And so now it becomes a Kb problem. Like I said, things change a lot. And then the good news is region 4 or region D, I don't care what you call it, it's back to just being a boring limiting reactant problem. And you're going to figure out the pH from the concentration of the excess hydroxide. So 1 changes, 2 changes, 3 changes, 4 doesn't change. Are you ready?
Yeah.
Okay. So here is the IGC example, all right? So you were taking 0.5 molar formic acid. There's its Ka. And you're going to titrate it with 0.5 molar strong base sodium hydroxide. They've been very kind to you at this point, and I will point out that the molarities are identical. It does make one of their steps a little easier. Region 1, you're just going to figure out what the pH of 0.5 molar formic acid is. It's a Ka problem. Then they want you to go to the half equivalence point. And I'm happy with this. I'm happy to show you how this works, because this is actually what you do in the titration lab. You're going to calculate the pH at the half equivalence point. What is the half equivalence point? Well, duh, it's halfway to the equivalence point. At the equivalence point, we're going to be 1-to-1 mole-to-mole ratio. But it's not 7, because these aren't strong acids and strong bases. What you end up making is 1 equivalent of the conjugate base, so it ends up being a Kb problem. And again, this is probably, in my experience, where students have the hardest time. And at the end, again, you're just going to have excess hydroxide in there, and you're just going to figure out the pH based on the excess hydroxide concentration. So they've got this going. We're starting with 40 mils of 0.5. Again, for number 1, you don't have to worry about the 40 mils. You're just going to set up a Ka problem and calculate the pH of 0.5 molar formic acid. So Ka is going to be equal to, I mean, you can set up the ice table. Set up the ice table if you need to, okay? Set it up if you need to. Whoops, didn't mean to do that. Set up the ice table if you need to. If it's H, CHO2 plus water in equilibrium with hydronium. Remember, it's a weak acid. And this is important, this CH2O anion. All right. And you do the ICE thing. And this one should be super easy because we haven't added anything extra. So this is just 0.5. We don't care. That's 0. That's 0. That's plus x. That's plus x. We get an x, and we get an x, and we get minus x, and we get 0.5 minus x. Okay, blah, 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 right? Whoops, sorry, minus x. Blah, 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 blah. This is small enough. The 0.5 is large enough. The hack is in effect. And you end up with the hydronium ion concentration, which is x, equaling the square root of 0.5 times the Ka. All right? And we've been doing these. You need to be good at this one because we haven't even added anything in yet. And you can see that the pH, instead of being, way down in the digits less than 1, about 2.02. 2 sig figs from the Ka, 2 sig figs in the pH. All right, everybody with me?
Yeah.
All right. Carrying on. At half of the equivalence point. Now, like I said, it was very kind of them to make these molarities identical. But guys, you've just added a strong base to a weak acid. It's not reversible. It's going one direction only. So this is an initial change, final. This is stoic, not Ka and Kb yet again. So do this in moles. Do it in moles, do it in moles, do it in moles. And so you're going to have to figure out 40 milliliters of 0.5 molar, 40 milliliters of 0.5 molar. I get a 0.0200 moles.
Yeah, I got the same.
Okay, now half equivalence point. I kind of helped you with the math here. If we're at the half equivalence point, that means we're halfway to the 1-to-1 stoich. So this would be 0.0100 moles. Does that make sense?
So you just literally half the milliliters?
Yep.
Oh.
In this case, just half the number of moles. And because the concentrations were the same, it ended up being half the number of milliliters.
Oh, okay.
Okay, if that makes sense. And then over here, this is utterly critical now, right? Before we weren't even paying any attention to what was on the product side, right? Because we just kept making water and a salt, right?
Yeah.
Well, no, we have a problem, not a problem. We have an important issue. That's the conjugate base. So we're about to make a permanent buffer. Do the math. Who's the limiting reactant? Right? We're before the equivalence point. So the base is the limiting reactant. It's going to get consumed entirely. An equivalent amount is going to get consumed of your weak acid. You're going to do the math.
0.01.
Right. Yep. Your limiting reactant's totally gone. And you're right. What you have left over of the weak acid is 0.01 molar or 0.01 moles, right? But guys, you got to do the math over here now too. Before, all we were making was water and a boring salt. No, now we're making conjugate base. So if we consumed 0.0100 moles of hydroxide, then it means we made 0.0100 moles of the conjugate base of the formic. And all of a sudden in the beaker, you have 0.01 moles of a weak acid and 0.01 moles of its conjugate base. That's a buffer. You just literally, by doing the titration of the weak acid with the strong base, you just made a buffer. Victoria, that's why the beginning point parts of that titration curve looks so different. We've just made ourselves a buffer. And the pH. So that's the bad news, is you're going to have to be able to spot the fact that you just made a buffer. But here's the good news. pH equals pKa plus the log of this concentration over this concentration. All of a sudden, you can use the Henderson-Hasselbalch again. Congratulations. pH equals pKa plus log of 0.01 over 0.01. Quick, somebody do the math. I've got that many moles of that many moles of his conjugate base, and I just plug and chug it into here. When I say you have to be able to spot whether you've made a buffer or not, right? You have to be able to spot whether a system is a buffer or not. This is why. Because if you just made a buffer, you can use the Henderson-Hasselbalch, and then it's pretty easy. pH equals pKa, which is 3.74, plus the log over 0.01 over 0.01, which is the log of 1, which means at the midpoint for the titration of a weak acid by a strong base, at the midpoint, and that is what we call this, half the equivalence point, also known as the midpoint. The pH equals the pKa. If this was not a 1-to-1 ratio, then it's going to be a little off. But it's still going to be a buffer unless we go beyond that 10-to-1 limit. So that's what you have to do in region number 2, or region number B, as your textbook calls it. The first region is just a Ka problem. The second region, it's a buffer problem. And you've got to do this stoich to figure out the ratio of conjugate acid to conjugate base. And then at the equivalence point, something else has happened. Oop, I think that number's wrong. Oh, no, that number isn't wrong. Sorry, my bad. At the equivalence point, so region 3 or region C, I don't care which one you call it. At the equivalence point, you've done, and I still don't like the looks of this slide. At the equivalence point, you've done CH2O plus the OH minus to make the CH2O minus plus water. That's how the titration is working out. Well, look, at the equivalence point, you have just the right amount of this and just the right amount of that. Stoichiometrically, it's perfect, which means that the only thing you have left in the Erlenmeyer is this. That's been completely consumed. That's been completely consumed. That is the definition of equivalence point when they are equimolar. So the only thing left in the beaker is the weak conjugate base. The weak conjugate base turns around. If I can get this out of the way so I can see. The weak conjugate base turns around. Whoops, sorry, my bad. The weak conjugate base turns around and is in equilibrium with the water. And all of a sudden you're stuck with a KB problem. At the equivalence point, you have a KB problem. You're going to have to figure out the initial concentration, right? The concentration of the conjugate base at the equivalence point is going to be whatever it took this many moles divided by the total volume is going to give you a new molarity. And that's how you start to set up this ice table. And this one is an ice table because it's just a KB. You used up all the hydroxide. You used up all the formic acid. All you have in the beaker, all you have in the Erlenmeyer is the formate, is the conjugate base. And it's a KB problem. Now, KB problems, not that bad. Negative, plus, plus. Probably the hardest part is getting the concentration. Sorry, get the X in there. You get 0.25 minus X, 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 and you're back to calculating a KB. But for most of you guys, this is the hardest part of this. Is at the equivalence point, setting it up so that you realize that all that's left in the Erlenmeyer is the conjugate, getting the correct concentration, molarity of the conjugate, and then starting the table again, the ice table again with the conjugate. And you work your way through this thing. And you end up with this because KB is going to be equal to X squared, oops, sorry, X squared over 0.250 minus X. The KB is tiny, so you know the hack's in effect. And remember, this X squared hydroxide is equal to X, which is going to be equal to the square root of that concentration times the KB. You're going to calculate a POH. You're going to subtract it from 14. It's the equivalence point that's hardest for most students. We're going to do it again. You get to region 4, to that fourth region. Again, now you're just setting up an ICF table again. You're figuring out how much excess base is in the system. And the excess base is coming from the hydroxide, so that makes this calculation really easy. It's the same as it was before. Did I lose everybody?
No.
No, yeah, no, you're like, no, but I'm like really way too much crap. Yes, exactly, really way too much crap.
There's a lot going on.
There's a lot.
What's going on?
There's a lot going on.
Ooh.
It doesn't matter whether you're in the classroom or not, right? There's a lot going on now. So yeah, no, it's hard to keep up. No, you're exactly right, Daniel. It is hard to keep up. So everybody shake your head out.
We're
Yeah.
doing another example of this.
Exactly. So
Okay.
well, if you were able to print that, let's do my example. What we just did was the IGC example, okay? So you can go back to the textbook and they're going to walk you through this. Now we're going to walk through one more and then boy, I'm going to have pity on you and let you go. It'll be time anyway. But hopefully you're writing along because what helps, I mean, you just have to do it.
Mhm.
And if you've written it down on a template, document, and you know the template's right, and you've done it in your own style, then you're pretty sure. Yeah, I know being on Zoom does not help. But But then if you have an accurate template document in front of you, the process doesn't change for zone 1, zone 2, zone 3, zone 4. Just what changes is the KAs and KBs and the initial concentrations. And you can just kind of plug and chug from the template. So, ready to do my example?
Yep.
Sure.
Yeah. So, oh, sorry, Sophia, we're going back to generic acid HA, but we don't care, right?
Yeah.
As long as we have the Ka, we don't care. So we're going to do the 4 regions. So, you know, that cute little graph is going to look kind of like, it's going to start, you know, at a higher pH. It's going to go through that buffer region where the pH doesn't change very dramatically. By the way, that's why that titration lab is such a pain in the butt, is because you sit there for so long in a buffer region and the pH never changes. And then all of a sudden you get to 1 drop and bam, up it goes.
Oh,
And
yeah.
your equivalence point is sitting in there, but all this time you were just wondering if it was ever going to end. There are dozens and dozens and dozens of data points in there. And then it finally finishes off and it goes back to looking kind of like all the other ones do. Okay? So this is before we start titrating. It's just a Ka problem. This is before the equivalence point. It's a buffer problem. This is at the equivalence point. It's a Kb problem. And this is after the equivalence point. It is an excess reactant problem. And ready, set, go. Do the Ka. You've got your lovely equation. HA plus water. It's the only thing in the beaker. Making H3O plus and A minus. And this is an ice table. You start with, what did I start with? 0.5? 0.5, 0, 0, minus x, plus x, plus x. We get an x. We get a 0.5 minus x. We can see that x is negligible because the Ka is so small. And the hydronium ion concentration is going to be equal to x, which is equal to the square root of 0.5 molar times the 6.3 times 10 to the minus 5th. It looks like some Flexions numbers. So we only care about water. We're actually, honestly, Daniel, we don't ever care about water. What we have to care about is the amount of conjugate base.
Professor, I'm looking at this exercise on the worksheet, but I can't find the Ka written anywhere.
Oh, did I screw that up? No, look, one more example. So now you're on titrate, it's page 2. Titrate 10 mils of 0.5 molar HA with 0.4 molar sodium hydroxide. The Ka equals, you got it?
Yeah, I was at page 1. Whoops.
Oh yeah, go to page 2.
Got it.
Page 2. Right, because there is no Ka for page 1 because it was a strong acid, right?
Yeah, exactly.
Yeah, so there it is. It's 6.3 times 10 to the minus 5. And you plug and chug your way through this. Quick, everybody do it. 0.5 times
0.006 is what I got.
What'd you get?
0.006.
Yeah, but that's not enough sig figs.
0.0056.
I like that. So that's the molarity. All right. So now you take the negative log of that. And if you're me, what do you get? 2.25? I hope. Oh, look, 2.25.
Yeah.
Okay. So there's before the thing even starts. We've gotten nowhere yet. Now we're going to add a certain amount of strong base. What did I say? 5 mils? 5 mils. And we're going to set up this ICF table because it's going one direction and one direction only. And I'm hoping. Oh, look. Thank heavens. I put in my blank ICF table. I was hoping. You can see up top already, and this is for whoever asked before, because this one's in moles, which is fine because we can do buffers in moles. Since this is in moles, I've already calculated up here the number of moles of each reactant. I just took the 10 mils times the 0.5, and so I got the 0.005. Oh, there's too many sig figs. Sorry about that. 0.0050 moles. 0.0020 moles. Yeah, bad me. I've got too many sig figs up here. Oh well. And this right now is a 0, right? But now do the limiting reactant math. The hydroxide is the limiting reactant. We're going to consume it all. We're going to, Bob is groaning because even he doesn't like So, whoops. Oh, my bad. Bad me. 2. All right. So we're going to use all the limiting reactant. We're going to consume some of the excess reactant. But here, Daniel, here's where it's important. We still don't care about the water, but we so care about the fact that we just made 0.002 moles of the conjugate base. So this is gone. It's zeroed out. Here we've got a 0.0030 of the weak acid. And oh, hello, we've got 0.002 moles of the conjugate base. Now you can go through and calculate the hydronium ion concentration. Yeah, it was what we care about is the conjugate base. Yes, an equivalent amount of water is being formed, but seriously, we're not throwing it in the Henderson-Hasselbalch equation. We're throwing the conjugate base in the Henderson-Hasselbalch. So you can go through the traditional way and, calculate your hydronium ion concentration, blah, 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 blah. Or you can realize that the thing's a buffer. Hoorah. pH equals pKa plus log of base over acid. You can go straight to the Henderson-Hasselbalch. It is a buffer before the equivalence point. It's a buffer, it's a buffer, it's a buffer, it's a buffer. Use the Henderson-Hasselbalch. Why do you think I keep saying that so many times? Anybody?
A buffer.
Because you'll panic and forget to use it on the test. And you'll spend 20 minutes doing it the long way when you could have thrown it into the Henderson-Hasselbalch and be done in about 3 minutes. How many times have I seen that in my life?
Too many.
Too many. You get to use this, you get to use it, you get to use it, please use it. All you got to do is quickly, oh yeah, thanks. Just a reminder, it's a buffer. Thank you so much, Daniel. You know how hard I'm going to troll you if you forget to use it, Daniel. You know that, right? So now, what is the pKa of this goofy thing? 6.3 times 10 to the minus fifth. I don't even remember. 6.3 times 10 to the minus fifth. We take the log. I got a 4.20. Anybody? Is that right? 6.3 times 10 to the minus fifth. Take that log. I got a 4.20.
20.
Cool. Equals 4.20 plus the log of 0.0020 over 0.0030. I think you can do that math.
Hold the calculator, Ken.
Yeah, exactly. That too. whatever the log of 0.6667 is.
4.02.
I'll buy that.
Yeah, I got the same.
Here it is finished up. Right. Just so you know, on this, I even showed, oh, don't you have to turn it into molarity? Yeah, but they're this, but the volumes are the same. So you do it in moles instead. Right? And we save ourselves some time. You can do it longhand. You can do it the ice table way. Or sorry, not the ice table way. You can do it the Ka way, or you can recognize that it's a buffer and throw it into the Henderson-Hasselbalch. Take your pick. It doesn't matter. But this is so much faster. Okay? Buffer, buffer, buffer. So now you get to the equivalence point. So the first zone's okay, it's just a Ka. The second zone is okay, it's a buffer, just get the ratio of weak base to weak acid correct. Now you're at the equivalence point. You can double check my math, but you're going to find out that, yeah, that's a 1-to-1 mole-to-mole ratio right there. So you're at the equivalence point. Actually, I'm going to go backwards for a sec. Think about it. You could set up that ICF table if you really needed to. Hang on, I got to erase and move around. You can set up that ICF table if you really want to convince yourself that you know what you're doing, but it would literally be, again, HA plus hydroxide going one direction to make A minus plus water. One direction. That's an F, sorry. If you do, right, what you've got there is 0.0050 moles, 0.0050 moles. This is not a limiting reactant problem anymore, guys. We're going to use it all up. We're going to use it all up. And we're going to make that many moles of the conjugate base. So what you end up with is 0.0050 moles of A minus at the equivalence point. No weak acid, no strong base, just weak base in the Erlenmeyer. That's why this is now a KB problem. But this isn't molarity yet, it's moles. So you're going to have to add up your two volumes. You're going to have to do the 0.0050 moles of A minus over what, 0.0225? 225 liters of solution to get your concentration of your conjugate base. And I'm going to get something like 0.22 molar conjugate base. And now you're going to have to set up a KB table to figure out the pH of that conjugate base. It becomes a KB problem. This is going to make a mess. That's okay. Here's the finished part. Oh, look, I got it right. Now it's a KB problem. I got the KB from the Ka, and you set it up as a KB problem, and now this is a KB ice table again. You need to convince yourself, and if you have to put that ice table together, that's fine with me. If I went back there, I know I'd be doing ICE. I'd be doing 0.220, 0.22. Don't care. 0, 0, minus x, plus x, plus x. We're going to get a 0.22 and an x and an x, and the KB is equal to x squared over 0.22. The hydroxide is equal to x, which is the square root of 0.22 times the KB. You're going to get a hydroxide ion concentration. You're going to turn that into a POH, and you're going to get yourself a pH. This is the one, well, zones 2 and 3 that you need to practice, okay? And you just got to do it, and you got to, and don't do it mindlessly. Remind yourself where you are and what you've got in the Erlenmeyer flask, because otherwise you're gonna confuse yourself. Don't do this mindlessly. The rest of it's there, but you should end up with an 8.77. And yeah, these slides are on. Actually, I'm going to swap out the slides that are there and put these exact ones on. They're very, very similar, but I did make a few changes early this morning, and I just didn't get them re-uploaded. But what's there gets you the answers to this thing. But for zone 3, you should be getting a pH of about 8.77. Depends on where you round. I am not going to worry about, 8.78 versus 8.76. I'm just not going to worry about it. But that's what you should be getting. And it's a whole lot of work. All right? Fun, fun, fun?
Yeah.
Yeah. And you can see I can do this a million times. You're going to have to sit and do it. You're going to have to sit and do it. But for zone 3, you should be getting a pH of 8.77. We get to zone 4, and you're like, what a relief. Now we've blown past the equivalence point. This is still, again, we never did change this. This is still 0.005 moles of HA. But now you should be able to do this 0.0060 moles of OH minus. And you can set up that ICF table. Again, this is in moles. This is in moles. This is in moles. You're going to take your 0.0050. You've got your 0.0060 in there. We've got nothing. And we don't care. And now you can see that the weak acid is a limiting reactant. And so you're going to subtract that 0.500. You're going to subtract that 0050, excuse me. And it's true. You've made over here 0.0050. You have. If anybody caught that. But guess what? Sure, this is 0.0050. But look, you've got an excess of strong base in there. POH equals the negative log of the OH. This amount of weak base, now that there's a whole bunch of strong base in the Erlenmeyer, it's not even going to register. So we're going to have to take the negative log of this guy's concentration, which is 0.001. So he's what's left over, moles of OH. But you got to divide it by the total volume, which is 15 and 10, 0.0250. And you're going to end up with a POH. This now again, because there's a stronger base in the Erlenmeyer, this doesn't matter much anymore. This only matters when it's when it's the only thing in the Erlenmeyer, or when it's in there in combination with its conjugate acid. And you should be able to come down to and get, whoa, there it goes, there it goes, there it goes, there it goes. A 12.6 again, which is actually, I believe, identical to the strong acid, strong base, because I did this with equivalent molarities and equivalent amounts. But in the first one, it was a strong acid, and in the second example, it's a weak acid. Are you now officially wildly overwhelmed?
Yeah.
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 A bit.
I did not expect to be doing this one on Zoom.
Excitement grows.
Feel free to imagine how much of the chalkboard I would have used on this example. But this is what you've got. That almost sounds like Bob in somebody else's world. No. Those are the titration calculations, guys. I don't even need to move on to the next slide. I think that's it. I think that's truly all yeah. Okay. Oh yeah, like I'm gonna make you do it the other direction. Okay. Yeah, sure, let's do it this direction now. I did pull that question out. Yeah, exactly. I did pull that question out of sapling. It would again be the reverse. You'd do the KB of the untitrated base, then you'd have yourself a buffer, then you'd have a Ka of its conjugate acid, and then you'd have just the pH from the excess acid. It is literally the reverse. But I have found that if you can do it in one direction, should you have to take a 300 or 400 level course and do it again, hypothetically at uni, would they expect us to know how to do it in reverse? Mo, if you're going to go take the 300, 400 level.
Oh, what's up?
And analytical, yes. All right. But honestly, if you can get the forward direction, the one we've done, if you can get the forward direction going, by the time you get to those courses, it'll be fine. You will be able to do it. All right. And it's going to be in a quant or an analyt kind of class. All right. So get it for me in the forward direction. So titrate weak acid with strong base, titrate strong acid with strong base. 4 different regions. Now you're thinking that the strong acid with strong base looks trivial. It's just all Chem 111 stoic. But this weak acid with strong base, you got a Ka, then you got a buffer, then you got a Kb, and then you've got excess hydroxide. And that's the way to just kind of, that's your little mantra. All right. Ka, buffer, Kb, excess hydroxide. And give it a shot on the problems in the textbook. Gee, can you imagine what this next problem-solving assignment looks like? I can't imagine what kind of questions will be on that problem-solving assignment. And then there is the one of, I think just one of each, but the big monstrous sapling online questions like this. Okay, in my personal opinion, I would recommend doing the sapling problems like this last, because sapling's not going to give you partial credit. for showing your work, and I am. So get it right. Get it right on the textbook problems where you've got a template. Get it right on my problem solving assignment where you've got a template, and then launch your way into the Sapling online homework. Make sense?
Yeah.
Okay. Unless somebody else has got any clarifications they want, I am going to let you guys go chew on this. I did realize again this morning, and I still haven't changed it. I have officially pushed back that due date for the individual research assignment. All right. It was supposed to be what, this Sunday?
Saturday, I think.
It's Saturday. I'm kicking it back a week. All right. I'm kicking that back a week, but you've got the other problem solving assignment for me. I'm going to upload this problem solving assignment. And then please don't forget, now that we've done titration calculations, you owe me a titration lab. Oh, and right. Yeah. The number 7, problem solving number 7. Is that what, oh God, where are we? Yeah. Is due tomorrow night, right?
Yes.
Okay. This next one that I haven't posted yet, look, I'm going to give you probably an entire week for it. Okay. And I'll get it uploaded tonight or tomorrow. But it'll be all this titrating stuff and this making and trying to mangle buffers questions. Okay. But then you've got the titration lab. So you're going to watch the cute little video of Dr. Solmanathan. I've already uploaded the Excel data pairs. You are literally going to graph that pH curve. You're going to be calculating pHs at midpoints, pKa's, concentration of the weak acid itself. It's a good application of a lot of what we've just gone through. Oh yes, and the pre-lab quizzes. Just because, yeah, why not? You want the points, right? It's not like I'm going to tell, at this point, it's not like I'm going to tell you you can't do the lab because you haven't done the PLQ. But I am going to turn those PLQs off. And that is to just keep you guys doing what you're supposed to do. And again, Daniel, I think you came in a little late. Officially right now, the pass-fail thing, the chancellor of the VCCS says, yes, we're going to pass-fail, but the president of Northern Virginia Community College says, let's wait for further guidance. We are all really, really, really hoping that you students are going to be given the option of either doing the course pass-fail or doing the course with a letter grade. We are really, really hoping, but we don't have we don't have that information yet. I think they're still struggling with how to make it happen. Yeah, I know, Pasha. It shouldn't be right. It shouldn't be forced. I have a feeling. Sorry, that's it. Those are allergies. I have a feeling they're trying to figure out the technology logistics of it. How do they allow you guys to make the choice? Since it's all on SIS. And SIS was coded in, I think it was coded in COBOL. For those of you in the computer world, I think that's in COBOL. It's not even in Fortran. I think it's in COBOL. My better half or other half, whatever you want to call him, the grumpy guy I share an office with, he just gave me a thumbs up and he's like, yeah, dear, it's probably in COBOL. You guys don't even know what COBOL is, do you?
Nope.
It was the world's most awesome programming language.
One step above basic.
It's one step above basic, but it was so wordy that I swear to goodness, you learned to program in COBOL and you would literally, type in, please program, if you would be so kind, could you now sort these values based on last name? It was just amazing.
Hmm.
But,
Programming
yeah.
for history majors.
Yeah, programming for history majors. That's what we called it. It was awesome. But anyway, another meme. Oh, now Michael, we've got Michael going on the meme thing, guys. Quick, somebody save a couple of those. Anyway, is there anything else from any of you? Shall I let you go to eat lunch? Yes, memes. Memes,
You're
memes,
not
memes.
recording these lectures, right?
Somebody is. I'm not.
Okay, and I think Abdul posted it, so yeah, I guess I'll get it from him. But
Yeah, you guys figure that out yourselves. I don't care. Since you can't see my face, I don't care.
Professor,
Yes, ma'am.
so do you know if they're going to like keep March 30th as like the registration for like the summer session, and if they're going to continue with remote instruction?
To the second question, the answer is yes, summer is remote.
Is that for every college?
I believe the answer is yes.
And they're not certain about the
Oh.
full semester, right?
They're not certain about what?
The full semester, I'm guessing.
What, the full summer?
The fall, like
Oh,
fall.
fall, autumn. Yes, fall 2020. No, there is no guidance on fall 2020.
Oh,
But
all right.
currently, everybody I know who's teaching summer 2020, they've been told it's going to be remote.
Oh, all right.
I know.
Oh, wow.
Oh,
But just in
And if it's
Virginia or
different-
everywhere?
If it's us, then it's VCCS, which means it's all of Virginia.
Okay.
Oh, and I've just been told that Maryland is also going remote all summer long.
Oh, wow.
But what was the first question? Oh, the
You
March
happen to
30th.
know?
You're right,
Yeah.
the March 30th registration. I don't know. Shall we all look it up? I wonder if they. My guess is that they've changed it. And
I
my
saw a page like when I Googled it, but then like it said error. Like, yeah.
error, like we have no idea.
They
what's
might have
going on
taken the
anymore.
page down because they're not certain. I don't know. I'm guessing.
Let me see. Have they changed the academic calendar yet? Let me see what pops up for me. Academic calendar, spring, fall, summer. Summer open registration for all students, April 13.
Oh, April 13th. Okay.
Now, fall priority. Whoa, it's not even up yet. Yes, Bob, we hear you. You're tired. I wonder if I have access to that. Give me a sec. No, they've pulled. I think they've taken it down, guys.
Hmm.
Fall 2020. I'm not finding it anywhere. Is anybody else finding it?
No.
No. So summer 2020, we kick off everybody. You know, it's just a scrum on the 13th,
Okay.
and then whenever it starts. When does it start? Oh, there it is. 18th, the 18th still. But yeah, that will be remote.
All right.
Okay.
Mm-hmm.
Yep, it will be remote instruction. At least people will have a little bit more lead up time, but yeah, everybody's going to be online. Anything else? Should we all go
No.
and get lunch?
Yeah.
Yeah. Okay. And as I promised, I'll figure out the virtual office hour thing. I'm getting there, but you know how to get a hold of me. Right?
Thanks, Professor.
Thank you for everything, Bob.
Whoop, that was fuzzy. Whatever that was. Yeah, otherwise I will see. Yeah, exactly, Daniel. My ears. Otherwise, if there's anything else, holler at me. Otherwise, please practice this and get outside because the weather's improving and shake your head out. Okay?
Will do. Thank you.
All right, welcome.